Hi guys, welcome to chemistry. This is Unit 2, a study of matter and energy. Pretty much everything in the universe can be classified as either matter or energy. Matter is stuff, things that you can see, things you can touch, things you can feel, and energy is the things that are the forces that affect that stuff. Some introductory definitions. First off, this is one of my least favorite definitions in the world because it uses other definitions, but matter is anything that has mass and takes up volume. You'll hear me refer to it a bunch as stuff, things, tangible things that you can pick up. Your car is matter, you are matter, the air is matter, water is matter. So stuff is matter. So what is mass? Another crappy definition, the amount of matter in an object. How much stuff is inside something. Very dense things like lead weight are going to have lots of matter, whereas very light things like a balloon won't have as much matter in them. So mass is the amount of matter in an object. Now, most of the time, we measure mass by weight. If you want to find out how much matter something has inside of it, you put it on a scale and you measure weight. But you aren't really measuring mass when you measure weight. You're measuring gravity. Weight is the pull of gravity on an object. In outer space, you lose weight, but your mass is still the same. Weight is gravity. Mass is how much stuff there is. And volume is how much space an object occupies. Back to my balloon and lead weight example. Lead weight might have a whole lot more mass, but be a whole lot smaller. Whereas a balloon doesn't have much mass, but it takes up a lot of space. Volume is how much space an object occupies. There's my little puffer fish. Not much volume, lots of volume. Units for volume are either going to be liters, decimeters cubed, milliliters, or centimeters cubed. In this class, we most of the time just use liters or milliliters. Decimeters cubed and centimeters cubed are usually for solid things, more for math class. You might see them every once in a while, mainly just know not to use liters cubed. The other thing that we're going to talk about in this unit is states of matter. You guys have been studying this since kindergarten probably. You got three main states of matter: solid, liquid, and gas. You're going to understand later on exactly what makes something into each of those categories. So what is composition? Composition is pretty straightforward. Composition is what matter is made of. You're composed of a whole lot of water and a whole lot of carbon. What things matter is made of is the composition. Water is composed of hydrogen and oxygen. Sugar is composed of carbon, hydrogen, oxygen. So composition is what matter is made of. So example here, copper is made up of a whole bunch of copper atoms, arranged like so. Water made up of lots of groups of 2 hydrogens and 1 oxygen. Properties. Properties describe the matter. So take a second and look at that apple. What are all the different ways we can describe that apple? Think about it a second. Probably said things like red, shiny, things like that. What it looks like is red. What it's shiny. What it smells like. It smells sweet once you cut it open a little bit. Its mass, you can put it on a scale, you can measure its temperature, whether it's hot or cold, things like that. But properties can also be how it behaves. What's going to happen when you set it on fire? What happens when you try to squish it? What happens when you drop acid on it? And this is all because everything's made of atoms. One of the basic things we're going to talk about in chemistry is how an atom is a basic building block of all matter. And one of the cool things about it is if you think of atoms like blocks of Legos, there's millions of different types of Legos that make everything in the universe, but there's only about 100 different kinds of atoms that make up everything that you know. Right? So those different types of atoms are elements. Elements contain only one type of atom. Monatomic elements, mono, one, consist of only one like atom bonded to itself. Or not bonded to itself at all, just unbonded. Things like iron, aluminum, copper, helium, a lot of metals are monatomic elements. Polyatomic elements consist of several like atoms bonded together. So you have, for example, diatomic elements, hydrogen, oxygen, bromine, fluorine, iodine, nitrogen, chlorine. Those guys like to bond to themselves, and we'll talk about bonding way more later. And then you also have some other things that will bond in strange combinations, like phosphorus and sulfur, P with 4 together, and then sulfur with actually 8 together. An allotrope is a different form of the same element in the same state of matter. It's a pretty wild thing, but you can actually have matter that is a little bit different because of its bonding. So, for example, we're very familiar with oxygen gas, and it's what you're breathing right now. It's what keeps you alive. Biology class, you might remember, it was in cellular respiration, aerobic respiration. And oxygen gas is O2. That's what we breathe. But if lightning bolt hits a molecule of oxygen gas, you actually can end up with O3, ozone. And ozone you don't want to breathe, but it does a pretty good job for us filtering out UV rays. That's where we get the ozone layer. Carbon can take up a lot of forms. Carbon we're going to talk about a bunch because it's what makes up living things, but elemental carbon looks kind of like just black powder. Graphite is what makes up your pencils. You know, we call them lead pencils, but they're really not lead. They're graphite. It's a type of carbon that's hardened a little bit, and that's why if you squish it up, it can look more like that elemental carbon. But then if you've ever seen the movie Jimmy Neutron, you know if you take that elemental carbon and squish it for long enough and give it lots and lots of time, you can actually have a diamond. Those are all three the same elements, but they're different forms based upon different pressures and different bonding formations. You also have something called a buckyball. Buckyball is just a giant multiple carbons bonded together, and it acts really strange, and scientists really dig that type of stuff. Now, once we start bonding atoms, you end up with a molecule. So let's look at some examples here. If you have one oxygen atom, its chemical symbol is going to be O, and a model might just be a circle. One oxygen molecule, O2, the model would be two circles pushed together. Now, if you had two unbonded oxygen atoms, you couldn't say O2 anymore because that shows that they're bonded. So two unbonded oxygen atoms are going to be 2O. And if we were to draw a model, two circles not touching. Same idea with phosphorus. Instead of circles, we'll use squares. One phosphorus, one square, one phosphorus molecule is P4. A model of that, 4 squares touching. And then 4 unbonded phosphorus atoms, you guessed it, would be 4P. 4 squares not touching. And got cut off a little bit there, but elements may consist of either molecules or unbonded atoms. So any of this combination works for elements. Now, when we start mixing together things, that's how we get most of the things in the universe, compounds. 2 or more different types of atoms. They have properties that are different from those of their constituent elements. Now, this is kind of hard to understand because if you take sugar and you take lemon juice, you mix it together, you got lemonade. You get the lemon taste from the lemons and you get the sweet taste from the sugar. But that's not how compounds work. Once you take elements and put them in a compound, they are completely different properties. Let's look at an example. Sodium. Sodium is Na, and that's what it looks like right there. It's a soft metallic cube. You probably have never seen any in real life because you're about to see why. Sodium by itself, when you mix it in a little bit of water, explodes very violently and very dangerously. So, like I said, you've probably never seen any sodium in real life. Now, another element, chlorine. Chlorine gas, once again, you probably have never seen it, probably never been around it. And when you say chlorine with the pool, you're not talking about chlorine, the element, you're talking about a chlorine compound. And chlorine is a poisonous gas. It was used in World War I as a main ingredient for the poisonous gas they used. It was also used in will eat your lungs out. It makes people cough up their lungs. It's a really bad thing. So you look at these two things. You got sodium, which is explosive in water, and you got chlorine that's a poisonous gas. So if you put them together, you'll get something that's poisonous and explodes in water, right? Wrong. You put them together, you get salt. You get the salt that you sprinkle on your French fries. It's just as safe as anything else that you come across. So once you put something in a compound, it loses its old properties and it gets new properties. Now in this class, we're not going to be altering any atoms, because atoms can only be altered by nuclear means. You don't want to change atoms. If you do, you get that. The atomic blast at Hiroshima. Boom. It's very complicated. And this is, some nuclear chemistry that we're not going to worry about. Now in this class though, we're going to alter molecules. That's chemistry. Molecules can be altered by chemical means. Chemical reactions, chemical changes. That's what we're going to do in this class. For example, this is dehydration of sugar. C12H22O11, 12 carbons plus 11 waters gives you sugar. Now, when you dehydrate sugar, you get those carbons that come out, and you get this nice tall guy right here. We'll watch some videos of this in class. Electrolysis of water. If you hook a battery up to water, it starts making bubbles. Well, what are the bubbles? If you shoot electricity into water, why does it make bubbles? Well, it makes bubbles right there because you're shooting electricity in it. You're getting hydrogen bubbles. You're getting oxygen bubbles. So what is a compound? All compounds have the same composition. All samples of a given compound have the same composition. So every sample of salt is exactly the same. It's 39.3% sodium and 60.7% chlorine. Now you notice that's by mass. It's not 50-50 because sodium is smaller than chlorine. Look up on your periodic table. So there's no one salt better than the other. All salt is exactly the same. Phosgene gas is another example here. I'm going to just do a quick math example. I'll fly past this, and you probably can skip it as well. But phosgene gas is made of carbon, 254 grams. We're going to multiply it by its percent, 12.1%, 0.121, same thing. You get 30.7 grams of carbon. Oxygen, 254 grams is our total, multiplied by its percent, 41.1 grams of oxygen. And chlorine. Got to add up to our total, so we can do the math like that. And we have phosgene gas, mustard gas, used in World War I, showing how the properties work. Let's do another example. We have a sample of butane, C4H10, 288 grams of carbon and 60 grams of hydrogen. We must have find, first off, the total mass of the sample. Now, that should be pretty easy. If I tell you have 288 grams of carbon and 60 grams of hydrogen, total mass of the sample, surprise, surprise, what are you going to do? You're going to add. So we end up with 348 grams. So how do you find a percent of each element in butane? Percent's pretty straightforward. You take your part divided by your whole. Now my part in this situation is my carbon, 288 grams of carbon, or 60 grams of hydrogen. My whole is going to be the same for both of them, 348 grams. So we're going to take our part, which is for carbon, 288 grams, divided by our whole, 348, and we end up with 0.828. Now for percents, all you do is move your decimal place 2 spots, and we end up with 82.8%. Hydrogen, 60 divided by 348, you end up with 0.172, 17.2%. Check your work, add them together, make sure they equal 100. Now we can also use that information to help us work on other samples. It says how many grams of carbon and hydrogen are in 24.2 gram sample. So we have 82.8% carbon, 17.2% hydrogen. You just multiply your percents right here times your grams, and you end up with your parts of your DEFRA sample. So how much carbon will we have? 24.2 times 0.828, 20 grams. And how much hydrogen will we have? 0.172 times 24.2, get 4.2 grams. And we're going to do some more examples of these in class. I'll put this up here real quick. You feel free to pause, check it out if you want to. But I'm going to roll on to classifying matter because this is going to be a good stopping point. So classifying matter, we can classify them as pure substances. Your book just calls them substances. They have a fixed composition. Their composition can't change, and they have fixed properties. Their properties can't change. There are two types of pure substances. You have elements, you have compounds. Elements are all the same thing off the periodic table. Compounds are a combination of more than one thing off the periodic table. They're chemically combined. They're always going to be the same. These are pure substances. Elements, compounds. The easiest way to kind of trick into this is if I give you a chemical formula, you know it's a pure substance. Now if I mix pure substances together, you end up with a mixture. This is not a compound because it's not chemically combined. Their compositions can vary. Their properties can vary. They're not chemically combined. And they retain their individual properties. So go back to my example I was talking about earlier with the lemons and the sugar. The lemons make something taste sour and the sugar make it taste sweet, and so you end up with something that tastes sweet and sour. Tea, coffee would both be examples. Orange juice. Salt water has the salt from the salt, and the water is obviously water. Air is a mixture. We usually think of it like one thing, but air's got a lot of different stuff in it. We filter out the oxygen, but it's got nitrogen and carbon dioxide and water vapor and all kinds of stuff in the air. It's a mixture. There's two types of mixtures we're going to work with: a homogeneous mixture or a homogeneous mixture, also known as a solution, and a heterogeneous mixture. Homo, you probably learned in biology class, means everything's the same. So homogeneous mixture, the particles are so small that throughout the solution, everything's going to be the same. Properties are going to be the same throughout. It is evenly mixed. Salt water, you can't see the salt. It's there, you can't see it. Homogeneous. Kool-Aid, when made correctly. Now, if you make Kool-Aid and you still have sugar at the bottom, that's not homogeneous. But if you mix up the Kool-Aid and you can't see any different parts, homogeneous mixture, a solution. Now, if you can melt different metals down, you can actually end up making an alloy. It's a homogeneous mixture with metals. Bronze, pewter, brass. These are all examples. I'm sorry, I'm kind of ugly there. Bronze is copper and tin. Pewter is lead and tin. Brass is copper and zinc. It's a mixture of metals, alloy. A heterogeneous mixture is where you have different composition properties in the same sample. It's unevenly mixed. You can see the parts. Salad, you can see the tomatoes, you can see the lettuce. Heterogeneous. Raisin bran, you see the raisins, you see the milk, you see the bran. Heterogeneous. Now there's a special type of heterogeneous mixture. It's called a suspension. And a suspension, you can make it look homogeneous, but then over time it settles out. Paint's a classic example. Anything you have to shake or stir is a suspension. The one I like, the example I like to use is Yoo-Hoo. Yoo-Hoo chocolate drink. Before you open it, what do? Shake it up. It's a suspension. You can see the chocolate on the bottom. Let's look at this example here with 24 karat gold versus 14 karat gold. 24 karat gold means 24 out of 24 atoms are gold. It's pure gold. Everything is gold. 14 karat gold, 14 out of 24 atoms are gold. So let's look at this. Pure gold, mixture, gold and copper. Now why would you want to do that? Well, if anybody ever have been around pure gold, you know it's soft, it can break. So you mix in some copper, make it so it doesn't break, also make it a little bit cheaper. 24 karat gold is an element, pure substance. 14 karat gold is a homogeneous mixture, an alloy. 24 karat gold, periodic table, is AU. 14 karat gold is AU plus CU. So let's make a little chart here. We have matter. Everything is matter, period. Matter can either be a pure substance or a mixture. Pure substances can either be an element or a compound. Mixtures can either be homogeneous or heterogeneous. We're going to do a lot of projects and stuff with this in class. I hope you enjoyed the video. Sorry if I bored you guys. We'll do this, rock and roll with this in class. Take it easy.